Chapter 8. Delayed gastric emptying. Delayed gastric emptying reflects a breakdown in the coordination between chemical transformation, mechanical processing, and controlled release. The stomach is designed to hold material until it has been sufficiently altered, then deliver it forward in measured portions that match intestinal capacity. When this timing is extended beyond what is required for proper processing, the internal environment of the stomach changes, and the sequence begins to diverge from its intended pattern. The delay is not simply a matter of slower movement. It is a shift in how long material remains under conditions that were meant to be transitional rather than prolonged. The initial driver of delayed emptying is often a mismatch between acid availability and substrate load. When acid production is insufficient or delayed, proteins are not unfolded efficiently, and the structural reduction required for progression is incomplete. The stomach retains material in an attempt to continue processing, but without adequate acid, this extended retention does not achieve the necessary transformation. Mechanical activity continues, but it operates on a substrate that remains resistant, leading to a state where time is increased without a proportional increase in processing quality. Motility patterns adapt to this condition by reducing the rate of forward propulsion. The pyloric region remains more closed, and the release of material into the small intestine slows. This adjustment is driven by feedback that indicates the substrate is not ready for progression. At the same time, contractions within the stomach may become less coordinated as the system attempts to balance mixing with retention. The result is a pattern where material is held longer while being exposed to mechanical forces that do not fully resolve the underlying structural constraints. As retention increases, the internal environment of the stomach shifts. Prolonged exposure to partially processed material alters the chemical and physical state of the contents. Components of the meal that would normally move forward begin to interact within the stomach for extended periods, changing how they behave when eventually released. This can affect the consistency of the material and the pattern of release, leading to less predictable delivery into the small intestine. Downstream effects emerge as the intestine receives material in a delayed and often uneven manner. The timing of enzyme secretion and bile delivery is based on signals that assume a certain progression of gastric emptying. When this progression is altered, coordination is reduced. The intestine may receive smaller, intermittent releases followed by larger pulses, disrupting the alignment between substrate arrival and processing capacity. This variability affects enzymatic efficiency and absorption, contributing to instability in the digestive sequence. Neural regulation plays a central role in this process. Reduced parasympathetic tone lowers both secretory output and coordinated motility, creating conditions where the stomach retains material without effectively processing it. The system remains active, but its components are no longer synchronized. The delay becomes a compensatory state that reflects upstream deficits rather than an isolated dysfunction of movement. Delayed gastric emptying, therefore, represents a persistence of material within the stomach that exceeds the time required for proper transformation under aligned conditions. It is the result of insufficient preparation combined with altered coordination, where the system attempts to correct a deficit by extending retention. Without restoring the underlying factors that drive effective processing and timing, this extended retention continues to alter the sequence, affecting both the stomach and the stages that follow. Failed preparation leading to retention. Retention in the stomach is often the direct consequence of incomplete preparation rather than a primary failure of movement. The stomach holds material when the conditions required for progression have not been met. Acid exposure has not sufficiently altered protein structure. Particle size remains too large, and the chemical signals that indicate readiness for release are weak or inconsistent. Under these conditions, the pyloric region limits forward flow because the substrate does not match the requirements of a small intestine. The system is not arbitrarily delaying emptying. It is preventing the transfer of material that would be difficult to process downstream. This failure begins before the stomach has fully engaged. Weak cephalic activation reduces early acid output, and rapid intake limits both mechanical breakdown and anticipatory signaling. Food enters the stomach without having triggered the level of secretion required for immediate transformation. The stomach responds by increasing acid production after the fact, but this creates a lag where material is present without the chemical environment needed to alter it. During this period, mechanical mixing occurs on a substrate that remains structurally resistant, leading to uneven and incomplete preparation. As this condition persists, the stomach shifts into a retention mode. Contractions continue to mix contents, but forward propulsion is reduced because the signals that would normally permit release are not being generated. Larger and less processed fragments are held back, while only smaller portions may pass intermittently. This selective retention reflects an attempt to continue processing until the substrate reaches a state that can move forward. Without sufficient acid or proper timing, this extended processing does not fully resolve the structural limitations, and retention continues. The internal environment changes as material remains in the stomach longer than intended. Components of the meal interact under conditions that were designed to be transient, altering the consistency and behavior of the contents. The longer material is retained without adequate transformation, the more heterogeneous the mixture becomes. When release eventually occurs, it often does so in irregular patterns, sending unevenly processed material into the small intestine. Downstream coordination is affected by this irregular delivery. The intestine receives material that arrives later than expected and in forms that do not match its enzymatic capacity. Signals that regulate enzyme secretion and bile flow are based on timing that assumes proper gastric progression. When this timing is altered, these processes lose alignment. The intestine attempts to compensate, but the substrate it receives has already been shaped by prolonged and incomplete gastric processing. Failed preparation leading to retention therefore reflects a breakdown in the conditions required for progression rather than an isolated delay in movement. The stomach is holding material because it has not been adequately transformed, and without restoring the factors that enable that transformation, retention persists as a compensatory state. The sequence remains disrupted because the initial deficit has not been corrected, and each stage continues to operate on a substrate that does not meet its requirements. Protective slowing mechanisms. Slowing within the digestive system is not inherently pathological. It is often a protective response that emerges when the substrate entering the intestine does not match the system's capacity to process it. The stomach and small intestine adjust the rate of movement to prevent overload, limit exposure to poorly prepared material, and preserve the integrity of downstream processing. This slowing is driven by feedback that detects the chemical and physical state of contents, and it acts to maintain control over a sequence that would otherwise become unstable. The first layer of this protection occurs at the level of gastric emptying. When the stomach detects that proteins have not been sufficiently unfolded or that fats have not been properly prepared for emulsification, signals reduce the rate of release into the small intestine. The pyloric region maintains a higher level of closure, allowing only small amounts of material to pass at a time. This reduces the immediate burden on the intestine and creates additional time for ongoing gastric processing. The stomach is attempting to improve the condition of the substrate before allowing it to move forward. Within the small intestine, slowing continues as a secondary response. When partially processed material arrives, local sensing mechanisms detect the mismatch between substrate structure and enzymatic capacity. In response, motility patterns shift to increase contact time between the contents and the intestinal lining. This extended exposure allows enzymes more opportunity to act and gives absorption mechanisms additional time to extract available nutrients. The system is compensating for reduced efficiency by increasing duration. Chemical signals play a central role in coordinating this slowing. The presence of fats, larger peptides, and other incompletely processed components triggers the release of mediators that influence both gastric and intestinal motility. These signals reduce forward propulsion and adjust the timing of subsequent releases from the stomach. The effect is a coordinated reduction in speed that spans multiple segments of the digestive tract. When signaling is aligned, this slowing is precise and proportional to the state of the substrate. However, when upstream preparation remains inadequate, protective slowing can become prolonged and less effective. Extended retention in the stomach does not resolve structural resistance if acid levels are insufficient, and prolonged contact time in the intestine does not fully compensate for limited enzymatic access. The system continues to slow movement in an attempt to regain alignment, but the underlying conditions remain unchanged. This leads to a state where time is increased without a corresponding improvement in processing quality. The consequence of sustained slowing is a shift in the internal environment. Material remains in contact with the intestinal lining for longer periods, and microbial interactions become more pronounced as substrates persist within the lumen. These changes introduce additional variables into the system, influencing motility, secretion, and absorption in ways that further complicate the sequence. The protective mechanism begins to contribute to variability rather than stability. Protective slowing mechanisms therefore represent an adaptive response to upstream failure. They are designed to preserve function by reducing the rate at which the system is challenged, but they do not correct the initial deficit. When early-stage preparation is restored, the need for slowing diminishes, and the system returns to a pattern where timing is governed by coordinated processing rather than by compensation. Fermentation and pressure buildup. When material remains in the digestive tract longer than intended or reaches distal regions without adequate processing, microbial fermentation increases and changes the physical state of the lumen. Substrates that would normally be reduced and absorbed earlier become available to microbial populations, which metabolize them into gases and smaller chemical compounds. This process is not inherently disruptive, but when it is driven by excess or poorly prepared material, the rate and volume of gas production increase beyond what the system can easily manage. The result is a rise in luminal pressure that affects both motility and the perception of discomfort. Gas accumulation alters the mechanical environment of the intestine. As pressure builds, the intestinal wall stretches, activating sensory pathways that signal distension. This distension can modify motility patterns, either slowing movement to reduce further accumulation or triggering irregular contractions that attempt to redistribute or expel the contents. These adjustments are reactive and depend on the local conditions within each segment. The coordination between propulsion and processing is reduced because movement is now influenced by pressure rather than by the normal sequencing of digestion. The distribution of gas within the intestine also affects how contents are mixed and transported. Pockets of gas can separate regions of the luminal contents, creating areas where enzymatic contact is reduced. This further limits the breakdown of substrates that are already incompletely processed. At the same time, pressure gradients can shift the movement of fluids, altering the consistency of the contents and influencing how easily they can be propelled. These changes add variability to a system that is already operating under constrained conditions. Chemical byproducts of fermentation contribute to this environment. Organic acids and other compounds produced by microbial metabolism modify the pH and interact with the intestinal lining. These changes can influence both motility and secretion, reinforcing the effects of mechanical pressure. The intestine responds to these signals, but the responses are shaped by the altered conditions rather than by the original design of the digestive sequence. As pressure builds and motility adjusts, the timing of movement becomes less predictable. Material may be retained in certain regions while moving more rapidly through others, creating a pattern where processing and propulsion are no longer synchronized. This variability affects absorption, as some substrates may not remain in contact with the intestinal lining long enough to be fully taken up, while others are exposed for extended periods without achieving complete breakdown. Fermentation and pressure buildup, therefore, represent a downstream consequence of incomplete upstream processing combined with altered transit. The increase in microbial activity and gas production changes the mechanical and chemical environment of the intestine, influencing how material moves and how effectively it is processed. Without restoring the conditions that limit excess substrate delivery to these regions, pressure and its associated effects continue to shape the behavior of the system. Transition failure between stomach and intestine. The junction between the stomach and small intestine is a controlled handoff where material that has been chemically and mechanically prepared is delivered into an environment designed to complete digestion and initiate absorption. This transition depends on alignment between what the stomach produces and what the intestine is ready to receive. When that alignment is lost, the interface becomes a point of failure rather than a point of continuity. The intestine receives material that does not match its operating conditions, and the sequence shifts from coordinated progression to reactive adjustment. The stomach is responsible for delivering a substrate that has undergone sufficient acid exposure and mechanical reduction. This preparation determines whether enzymes in the small intestine can access and complete the breakdown of macromolecules. When proteins are not fully unfolded or when fats remain in larger aggregates, the material entering the intestine carries structural resistance. The intestine is equipped to finish digestion, but it is not designed to initiate the level of transformation that should have occurred upstream. The mismatch begins at the moment of entry. Timing is central to this transition. Gastric emptying is normally synchronized with intestinal signaling so that enzyme secretion and bile delivery are aligned with the arrival of partially processed material. When this timing is disrupted, the intestine receives material either too early, before adequate preparation has occurred, or too late, after prolonged retention has altered its structure. In both cases, coordination between stages is reduced. Enzymes may be present without appropriate substrates, or substrates may arrive without sufficient enzymatic or biliary support. The chemical environment at the interface also depends on this alignment. Material leaving the stomach carries the conditions created by gastric processing, including its degree of acidification. The small intestine adjusts its own environment in response to this incoming material, regulating pH and enzyme activity accordingly. When the composition of the gastric output is inconsistent, these adjustments become less precise. The intestine must respond to a variable input, and the stability of its internal conditions is reduced. Motility at this junction reflects the same dependency. The controlled release of gastric contents is designed to match intestinal capacity, allowing for steady progression. When release becomes irregular, the intestine experiences fluctuations in load. Smaller amounts may be followed by larger pulses, disrupting the timing of enzymatic activity and absorption. The system compensates by altering transit speed and secretion patterns, but these compensations do not restore the original coordination. The consequences of transition failure extend through the remainder of the digestive tract. Substrates that are not properly matched to intestinal capacity continue forward in partially processed forms, influencing microbial activity, immune signaling, and nutrient absorption. Each downstream stage inherits the effects of the initial mismatch, and variability increases as the sequence progresses. Transition failure between the stomach and intestine, therefore, represents a breakdown in the continuity of the digestive sequence. It is not a problem confined to either organ, but a failure of coordination between them. Restoring this transition requires aligning gastric preparation with intestinal readiness so that material is delivered in a form and at a time that allows each stage to operate within its design parameters.